All right, let us start with the new topic, that is beta, denoted by this, and gamma functions. So the gamma is denoted like this. Okay, so let me first tell what are the applications. Why do you need such functions? They're actually the special functions. All right, they're not commonly used. The major application comes into place when we are not able to solve a given integral. Okay, I have some integration coming up, and none of my standard integration procedures are can be used to solve that. In such case, we'll use beta and gamma functions to solve such integration. It's actually a integration tool. Okay, both functions are related to each other. That's why we study under the same heading. Okay, all right. Now, so let's define the definition of both functions. So the first function, that is a beta function, is defined for two variables. The first variable is m, second variable is n. So beta of m comma n is defined in the following fashion. Okay, one using a linear scale, that is integral from 0 to 1. It is x to the power m minus 1 into 1 minus x to the power n minus 1 dx. Right, the condition we have here, both m comma n will be greater than 0. It's a positive number. Okay, this is called as a beta function. The same beta function can also be represented by using the trigonometric identities. Right, we should be able to represent using the trigonometry. So how to do that? So this is also equal to, now I write the trigonometric. Both forms are necessary for us to understand and explore the properties and solve problems. All right, so we need the second one. This is actually another definite integral for theta varying from 0 to pi by 2. Okay, sorry, there is a 2 outside. 2 times integrals 0 to pi by 2, that's a theta varying from. This is sine to the power 2 times m minus 1, right, times theta, right, theta is my variable, into the cos function, cos to the power 2 times n minus 1, because still this is m and n are the variables. I'm trying to represent using that. So theta, okay, into d theta. So these two equations represent the beta function. Okay, that's the first thing. Right, very similar to this, I have another standard function, that is a gamma function. To write a gamma, I need only one variable, that is gamma of n. Gamma is a singular variable function, beta is two variable function. Okay, so very similar to the beta function, I have two representations. I can write this beta as well as the gamma functions using two forms. One is a linear format which uses ax, and the second format will be using the a different exponential notation. Okay, so first one is this, that is okay, gamma of n is integral, this is 0 to infinity e to the power minus x into x to the power, this is n minus 1 into dx. So here n will be greater than 0, indicating that this is a positive quantity. All right, now this is also can be written in a different format. This is 2 times integral 0 to infinity e to the minus of t square into t to the power 2n minus 1 dt. So these are the two formats using which we can write or we can define the gamma function. Okay, the definition is pretty important because we should be able to recall either of these four different forms of both the functions. Okay, now what we do, there are some properties. Since this is very new to us, we should know what are the properties, what properties they have. Okay, they show some very basic properties using which we can convert one to other, or we can have a good relationship that we can actually have. All right, so first we'll explore the properties of both. So this is about the properties. So first property, property number one, is related to beta functions. We are trying to relate the beta functions. If you have a beta function denoted as m comma n, this is also equal to a beta function of n comma n, right? In the sense, if you interchange m and n, right, the beta function will not change its ultimate value. That's what we want to prove now. Okay, so to start with, let's start from the LHS. Okay, LHS says that it is beta of m comma n. So what is beta of m comma n? I use one of the definition, that is integral 0 to 1. This is x to the power m minus 1 into 1 minus x to the power n minus 1 dx. Okay, so what I do, it's basically everything is integration, right? So what we do, we make a substitution now. So I try to put x is equal to 1 minus y, right? This implies if I take x to the other side, y should be equal to 1 minus x. Okay, so it means I have a dx in my equation. I should have a substitution for that. So to find that, I differentiate my first part of the substitution. That is, this implies the dx is equal to 1, there is a 1, differentiation is 0, minus y becomes a dy. In the sense, where I see a dx, after substitution, this dy will take its position. Okay, that is the meaning. Right. So I have to substitute for the limits as well. Okay. So it means the given limits are for x. Now I need to find what happens with y, because my substitution is in terms of y. So what I do, this implies when x is equal to 0, find out what is y. Y is equal to 1 minus x. So that is 1 minus 0. 1 minus 0 is 1. Similarly, I have other limit, that is x equal to 1, upper limit. Find what happens to that. Y is equal to, once again, 1 minus x. Now x is 1, 1 minus 1, so 0. So you see that x0 becomes y1, x1 becomes y is equal to 0. So I should indicate the same thing in my integration. So this is still equal to, in the sense, left hand side is equal to beta of m comma n. I'll write that once again. So this implies beta of m comma n is equal to, now you see the limits have been changed. It is 1 to 0 because now I am writing in terms of y. Okay, so this is y is equal to 1 to 0. So I'll write at the top just to indicate that this was x equal to 0. Fine. So y is equal to 1 to 0. This is 1 minus y to the power m minus 1. Okay, into there, wherever I see a 1 minus x, I should replace it with y. So the second term in the equation becomes, now it is y. Alright, so this is equal to y to the power, m and n are not changing, it's still the same. I'll write this is y to the power n minus 1 into dx is nothing but minus dy. Okay, after the substitution, now I'm going to use the property of an integration, that if you have integral a to b, you can reverse the limits provided you take a minus of that. This is equal to minus of, now I change y is equal to 0 to 1 because I flip. Flipping means minus will come out. There has to be one minus this. Okay. Now what I do, I write the y term first. Y to the power n minus 1 into 1 minus y to the power m minus 1 into minus dy, out of which I cancel this minus and minus. All right. So now this is equal to, right, I write this once again, integral 0 to 1, see y to the power n minus 1, 1 minus y to the m minus 1 dy. So if you have a term like this is x and this is 1 minus x, it still remains same. I would have called this, whatever is here, that's the first variable, this is the second variable, correct? So now you see m and n have been interchanged. Their positions have been interchanged, correct? So because of that, now I can write this function itself is the beta function, but the orders have been reversed. So this is equal to now beta function of n comma m, that itself is the RHS, right hand side of the property. Okay, so let me know if you have any doubt. Go to the second property. Okay, this is property number 2, and the property number 2, we look at a property of the gamma function. Okay, so second property is the gamma function of n plus 1 is equal to n gamma n. All right, this is first part of that, and I have another part to this. The gamma of n plus 1 is equal to n factorial for any positive integer n. If you have a positive integer n, then this refers to, right, n factorial. We need to prove this. Okay, fine. So let's start with the definition of the gamma function. So the definition of gamma function says gamma of n is equal to, I'm going to use one of the definitions which we have seen, integral 0 to infinity e to the minus x into x to the power n minus 1 dx. Okay, so but you see that what they have asked in the question is that you need to have gamma of n plus 1. Okay, so I'll do the same thing. This implies the gamma of n plus 1 is equal to, indicates that every n should be replaced by n plus 1. That's all. Okay, so we'll do the same thing. This implies it's the integral 0 to 1, 0 to infinity, integral 0 to infinity. I'm trying to write e to the minus x Okay, how about now? Can you see the screen? Continue. So I'm trying to write the gamma of n plus 1. So gamma of n plus 1 is equal to, right, gamma of n plus 1, this is equal to integral 0 to infinity e to the minus x. This remains as it is. I can touch only the n value. Okay, I cannot touch any other. So this becomes x to the power. You see that this is n plus 1. N is n plus 1, and there is a minus 1. okay, into dx. So this means this is equal to integral 0 to infinity e to the minus x into x to the n, x to the power n dx. Okay, so now when I have a product and I have an integration, what we do, we use integration by parts. Okay, but just before applying the integration by parts, I go with I change their positions because that will help me in the integration. Okay, so I write x to the n first, e to the minus x dx. You see, you have to see this is u into v, integral uv. Okay, so when I have integral uv, I'm going to use a specific technique of integration called integration by parts. So integration by parts is this: whenever you have a product, take the first term as it is. First term in this case, this is x to the n. Second term, whatever you have, you write, perform the integration of that and you write it. Okay, integration of that means, in the sense, it is e to the minus x, integration is minus of e to the minus x. Okay, this is one part of your answer. Directly you can substitute the limit 0 to infinity. This is not the final answer. I have one more part coming up. From this, subtract, minus, put the same limits 0 to infinity. Take the first term, you need to differentiate the first term, but before that, write whatever you got here, you have to write it over here. Okay, that means minus of e to the minus x will come over there. Okay, so my first term is minus e to the minus x. All right, I got this, minus e to the minus x. Okay, this is minus e to the minus x, the same term which I got earlier, into differentiation of the first term. First term is this, I have to write its differentiation. X to the n, differentiation is n into, differentiation is n into x to the power n minus 1. Okay, so I'm going to write n into x to the power n minus 1. But this, there is an integral, so you have to write dx. Okay, this is the property which we are using. You can call this, if you want to remember, this is called as integration by parts. This is called as integration by parts. Okay, now what I do in my next step, now since I need to substitute the value, you see that when you put x infinity to this, what happens? This becomes e to the power minus infinity. E to the minus infinity is 0. So when I substitute the limit, infinity is substituted, that means this is equal to 0. Okay, at the same time, when you substitute the lower limit, that is when you are going to put the 0 to this, it is 0 to the power n, right? 0 to the power any number is once again 0. So my first term of this result is completely 0. So what I do, I simply write this is 0 minus 0, indicating that I am substituting infinity first. That gives me a 0 over there. Then when I put 0 to this term, once again the term becomes 0. All right. When I go to the next term, you see there is a minus of minus, so this is plus. Okay, and there is a constant n here. Okay, so you can see that there is a constant n. Right, what I do, I write the n. Sorry, there is a constant n here after doing the integration. So I take the n outside, n into, this is integral 0 to infinity. I write the remaining term. This is e to the minus x, x to the n minus 1 into dx. Correct? If you refer back and check the definition of gamma of n, I have the same thing here, but n is there outside, n into gamma of n. Right? So this itself is the RHS. I started with the LHS, that is n gamma of n plus 1. Okay, and I ended up getting up n into gamma of n. That's my first part of the what you call proof, because the question said that there are two parts. So first part is done. Gamma of n plus 1 is n gamma n. Now we can extend this further, substituting the given particular condition. They have mentioned a condition saying that if at all you use this n to be integer, then we have a different answer coming up. Okay, so that means let's go to the second part. If n is an integer, right? I still start with the answer that I got just now, so I'll continue from there. Okay, so I know that the gamma of n plus 1 is n into gamma n. Okay, now what I do, I replace the n plus 1 by n. This implies okay, I'll call this is equation number 1. Gamma of n can be written as, you see, every n plus 1 is n, in the sense n becomes n minus 1, 1 less than that, n minus 1 gamma of n minus 1, correct? So this is 2. So now I put 2 in 1, what happens? The gamma of n plus 1 is equal to, there is a n initially in equation number 1, and gamma of n here, which can be replaced by n minus 1 gamma n minus 1. Okay, so I substitute that now. So the substitution looks like this. Okay, so n as it is, instead of gamma of n, I write n minus 1 gamma of n minus 1. I got this. So n minus 1 gamma of n minus 1. Right. So let me hold on to this. This is equation 3. I substitute for gamma of n minus 1. Gamma of n minus 1 can be written like, apply the same thing. 1 less than that, that is n minus 2 gamma of n minus 2. This is 4. Okay. What I do, I substitute 4 in 3. This gives me the gamma of n plus 1, which is on the left hand side, is equal to, there is a n, there is a n minus 1, and now I am bringing n minus 2 into gamma of n minus 2. This process actually can go further. It will grow. You see n minus 1, n minus 2, n minus 3, and so on. It will continuously grow till what number? Till you subtract the n minus 1 from that. In the sense, n minus 1, n minus 2, n minus 3 will go till, when you subtract, you may get 1, and ultimately you may get a 0. Correct? So until then this will grow. So I'll just write dot dot dot. This will grow in such a way that my final answer, I can try to write it in the following format. Right? This implies the gamma of n plus 1 is equal to, you keep writing n minus 1 into n minus 2 gamma n minus 2, but gamma n minus 2 could be n minus 3 gamma n minus 3, and so on. You see that when you subtracting one by one number, like you started from 70, 69, then 68, then 67, dot dot dot, ultimately you will come to what number? You will come to, say, 1. Okay, I'll write few numbers before this. Okay, so just to make sure that we understand this, let me write, say, I'll start from 3. Okay, so I have into 3 into 2 into, I write 1. Okay, when I write 1, what's the term? 1 into gamma 1, correct? See the last term. If at all the n minus 2 is equal to 1, 1 gamma 1 is what I'm going to get here, right? Instead of this. So I have a gamma 1 coming up. Okay, I don't know what's the value of gamma 1, right? But I need to find out that. So let me hold on to this now. So let's say this answer, this particular equation we got right now. let's call this as equation number, what was the last number? 4. So we'll write it as 5. Okay, so let me call this particular equation as equation number 5. Okay, now, so what I do, I need to substitute the value of gamma of 1. Once I have that, I can actually proceed further. Okay, so to substitute in this equation number 5, I find out what is gamma of 1. So gamma of 1, use the simple definition. Definition says it is integral 0 to infinity e to the minus x into x to the power n minus 1. So if n is equal to 1, this should be n minus 1. So n minus 1 means it is 0. Okay, x to the power 0 dx. So e to the power minus x is going to be minus of e to the minus x after integration with the limits 0 to infinity. So when I put infinity to this, there is a minus outside. I'll substitute these values. When you put infinity, this is 0. Okay, when you put 0 to the e to the power minus term, e to the power minus of 0 is e to the 0. E to the 0 is 1. So this is inside the bracket. I have a minus 1. Minus of that minus 1 is a plus 1. Are you okay? So we got this, which means the last term over here, gamma of 1 is nothing but simply 1, right? So this means, so I call this as equation 6. So 6 in 5 gives me gamma of n plus 1 is equal to, so you see that n minus 1, n minus 2, n minus 3, dot 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 up to 1 is nothing but n factorial into 1, because gamma of 1 is 1. So this means this itself is n factorial. Okay, this is possible only if we have n as integer. Then only I can do this. I can replace this as integers, right? Otherwise it's not not a factorial. If this is something like, say, 4 by 3, n is equal to 4 by 3, I don't have an integral I don't have the factorial coming up, because next n is 4 by 3, next number is 4 by 3 minus 1, next number is 4 by 3 minus 2, and so on, which is not a, I don't get the product as a what you call factorial. All right, so because of that reason, this is the answer. So if the n is an integer, gamma of n can be found easily by using a simple factorial. Okay, but if it is not that, then I need to use the formula which we derived before this, that is n into gamma of n. Okay, so this is the property number 2 of beta and gamma functions. All right, then let's go to the third and important property. Okay, this is property number 3, and this property is very important because it relates beta and gamma function. So the property is like this. Okay, beta of m comma n is equal to gamma of n into gamma of n whole divided by the gamma function of m plus n. You see that left hand side is beta, right hand side is gamma function. So if you are not able to solve any given integral using a beta function, definitely you can replace it by the gamma functions which is present on the right side. Okay, that's why it is very important. Okay, now let's go further. So in order to substitute in this particular in order to prove this, okay, let's define the different beta and gamma functions, okay, according to our requirement. So I'll start with what we know. Okay, we know that the beta of m comma n is written as 2 times, I'll use the other format, that is a trigonometric identity. Okay, 0 to pi by 2, this is sine of 2m minus 1 times theta cos 2n minus 1 theta d theta. Okay, call this equation 1. Now I define the gamma of first variable, gamma n, 2 times integral 0 to infinity e to the minus x squared into x to the 2n minus 1 into dx. Let me call this is 2. See, you have three different gamma functions. So I cannot use the same variable as per the basic rules of mathematics, right? I should not use the same variables if you have a product of integrals or something like that coming up. So I see that gamma n I define. If I want to write the gamma m, okay, if I want to write the gamma m, I should be using, right, a different variable. I repeat. So I defined gamma m. Okay, I defined gamma n. I defined gamma m and I defined gamma n. So what we do now, we try to replace the same thing by using a different variable, right? So that the variable which I'm going to use now is y. Okay, so this is 0 to infinity. I'll use y, e to the minus y square into, this is y to the power 2 times m minus 1 into dy. Nothing changes actually. Okay, only thing is that as per the rule I have to use a different variable, that's all. I'll use this, call this as 3. Okay, and again I know that there is one more function in the equation, which is gamma of m plus n. All right, so gamma of m plus n is 2 times integral 0 to infinity, right? I will use a different variable now. Let me say I'm going to use e to the minus, say, r square, right? Instead of y square, I'm writing r square into, see, this is r to the power 2 times, I don't have m here, I have m plus n, 2m plus n minus 1 into dr. Are you okay? Fine. So this is equation number 4. Let's hold on to this. Now, using 2 and 3, from equation 2 and equation 3, I have the following. Okay, that is, I multiply. Let me say gamma of m into gamma of n is equal to. So you see, 2 into 2, I just have to multiply which two equations? This is equation 1, this is equation 2. In the sense 2 and 3, I will multiply them as it is. Okay, so there is a 2 into 2. So that 2 into 2 is 4. There are two integrals, both are varying from 0 to infinity and 0 to infinity. Okay, fine. What's the next thing? I see that e to the power 2 numbers I have. Since the base is 2, in a sense, I can actually club them together. Okay, e to the power minus, there is a x square and y square. They get added up. X square plus y square. I already have taken minus outside. Okay, into, see, this is x to the power 2n minus 1, y to the power 2m minus 1. So x term remains as it is, 2n minus 1, y to the power 2m minus 1. The products are dx and dy. I got this. Okay, let me hold on to this. Let me say this is equation 5. Now I'll go for a substitution. Okay, substitution is, I put x equal to r cos theta. Okay, and I put y is equal to r sin theta. So this is very clear that why we substituted this, because if at all you do x square plus y square, you get r square cos square theta, r square sin square theta. Cos square plus sin square is 1, so you get a r square. Okay, and also we have another substitute. This is actually a standard procedure in integration. If you remember basics of integration, this is what we call changing the xy coordinates into r theta, polar coordinates. Okay, so there we have another standard substitution, that is dx dy can be substituted as r into dr into d theta. So r and theta are my variables now. X and y will be replaced by r and theta. Since you have double integration, both the variables needs to be replaced. Okay, right? And as per this, the variation of r is actually 0 to infinity, and the theta will vary from 0 to pi by 2. These are the changes I need to make in equation number 5. Okay, so making all these substitution, now you write 5. Equation 5 becomes, that is on the LHS I have gamma of m into gamma of n. Gamma m into gamma n equal to, you see there is a 4, I'll write outside. Integral, first integral I'll replace it as r varying from 0 to infinity. Okay, and the second variable, second integral, I'll replace it as theta. Okay, theta varying from 0 to pi by 2 as per my equation. So first term e to the minus r square, no change. X is going to be r cos theta to the power 2n minus 1, because first was x. So second term I'll write below this, into, now you see this is r sine theta, because this was y, to the power 2m minus 1. Okay, into dx dy. Dx dy is nothing but r dr d theta. Okay, I got this. Now this is equal to, now I shuffle them and I make things more clear. So this is equal to, first term is 0, r is varying from 0 to infinity, and second term is theta varying from 0 to pi by 2, right? E to the minus r square, we'll keep it as it is. Now you see I have the terms like r to the power 2n minus 1 and r to the power 2m minus 1. All right, so that is, I club both r's, that is over here and over here. Both terms have, one has this power, the second one has the other power. Okay, right, now I club them. So after clubbing, I'm going to get this particular answer. So that is into r to the power, I can, sorry, I'll change the color back to black. Okay, so this is r to the power. You can see that first term has 2m and next term has 2n, and there is minus 1 which is minus 2 plus this r. Okay, r is a plus 1, so minus 2 plus 1 is minus 1. So ultimately I'm going to write a minus 1 over here. Okay, so r to the power 2m, r to the power 2n minus 1. Okay, so this is minus 1. That's the term r. Then I'll write the sine term. So into sine to the power 2m minus 1 theta. I have a cos term 2n minus 1 theta into dr d theta. What I do now, I'll separate the integrals. How do I separate? I take a 2, because 4 will be split into 2 into 2. So first integral is 2 times integral r varying from 0 to infinity e to the minus r square into r to the power 2 times m plus 1 minus m plus n minus 1. Okay, because r to the power 2m plus 2n, I can take 2 outside, and this into dr. This is my first term. Into, let me write the second term now, that is integral theta varying from 0 to pi by 2, right? I have a 2 coming up. Okay, because 4 was split into 2 into 2. The second 2 comes here, into sine to the power 2m minus 1 theta cos to the power 2n minus 1 theta into d theta. Okay, I got this. Now you see that this is equal to, what is this? This is equal to, what is the first function? First function, if you see, this is, right, this is a gamma function. This is gamma of m plus n. Because since I have a m plus n inside this, it's going to be replaced as gamma of m plus n. Otherwise, if you have a single variable, it's a gamma n. Now I have a m plus n, so this is the case. Into this is beta of m comma n. So we actually tried to prove that we started from this was started with the gamma of m into gamma of n. Okay, so what I can write now, I'll take the gamma of m plus n to the other side. That means beta of m comma n is equal to, on the other side I already have gamma m into gamma n, and this will go to the denominator of the other side. Gamma of m plus n will go to the denominator. Okay, so that means this is equal to gamma of m plus n. All right, so that is our answer. So property number 3 also we have proved.